A model predicts, a system delivers value. Let me explain what that means. You can build the most accurate machine learning model in the world. It can score perfectly on every test, but if it just sits inside a Jupyter notebook and nobody can use it, it creates zero business value. So the real impact starts when your model becomes some part of something bigger, a system. A system that collects data, serves predictions to real users, watch for problem and keeps getting better over time. So in this video, I'm going to walk you through the difference between a machine learning model and a machine learning system. I'll explain what each one is, how they connect, and why thinking in systems is what takes you from a simple prototype to a product that actually moves business numbers. Let's break it down. Let's start from the basics. Machine learning model is at its core a mathematical function. You give it some input data, it looks at the patterns it has learned, and it gives you an output. That output could be a prediction, a classification, or a score. So, how do you build a one? The process goes like this. First, you collect data, then you create features from that data. So, features are just the specific pieces of information you want the model to learn from you. After that, you train the model, which means you let it study historical examples so it can find patterns. Finally, you evaluate how well it performs using metrics like accuracy, precision, recall, or AUC. These are the standard ways to measure how good a model's predictions are. Let me give you a simple example. Say you work at a subscription company and you want to predict which customers might cancel. That's called churn prediction. Your features could be things like how often a customer logs in, how many support tickets they have raised, how long it's been since their last purchase, and what subscription plan they are on. The model studies past customers, the ones who stayed and the ones who left, and learns which patterns are linked to cancellation. Then, when you give it a new customer's data, it can say something like, this person has a 78% chance of leaving in the next 30 days. That's very useful. The model is what I call the intelligence layer. It takes raw data and turns it into a decision. But here's the important thing to understand. The model by itself doesn't stop a customer from leaving. It doesn't send them a discount. It doesn't trigger a retention email. All it does is make a prediction. What happens with that prediction, how it gets to the right place at the right time, that's the job of the system. And that's what we'll talk about next. Now, let's zoom out and look at the bigger picture. Machine learning system is the entire setup that makes your model useful in the real world. It's not just the model, it's everything around the model that helps it work at scale, work reliably, and keep improving over time. So think of the model as the brain and the system as the full body that keeps the brain alive and connected to the world. First, you have data pipelines. These are automated workflows that pull in raw data from different sources like databases, APIs, or event streams, and then clean it, check it for errors, and shape it into a format the model can use. If your data pipeline is unreliable, everything downstream breaks. So this is your foundation. And next is the feature engineering and the feature store. In a production system, you need to make sure those features are calculated the same way during training and during live predictions. A feature store is basically a central place where all your features are stored, versioned, and served consistently. So this avoids a very common problem in machine learning called training serving skew, which is when your model sees different data in production than what it was trained on. Then you have model training workflows. In production, training is not something you do once and forget about. You set up automated pipelines that retrain models on new data, try different settings, and check the results before anything gets pushed to users. And after training, the model goes into a model registry. This is like version control, but for ML models. It keeps track of every version of your model along with its performance metrics and metadata. So if something goes wrong, you can always roll back to a previous version. Next comes deployment infrastructure. This is how your model actually serves predictions to users or other systems. It could be through an API, a batch job, or a streaming pipeline. We'll cover these in more detail in a bit. And then there's the monitoring. Once your model is live, you need to keep an eye on how it's performing. Is the accuracy holding up? Is the data still looking the same as what the model was trained on, is the response time was enough, and monitoring answers all these questions. And finally, feedback loops. This is where the system learns from its own results. The predictions your model makes, then the real outcomes that follow become new data that feeds back into the training process. This creates a cycle of continuous improvement. When all these pieces come together, you get four things that matter a lot in production. Scalability, meaning you can serve millions of predictions without things falling apart. And reliability, meaning the system works consistently even when the data changes. And continuous improvement, meaning the system gets smart over time without someone manually retraining every month. And measurable business impact, meaning you can actually tie the system's output to real numbers like revenue, cost savings, or customer retention. Now let's talk about how models actually serve prediction in the real world. There are four main patterns and each one fits a different situation. Let me explain them one by one. So the first is batch inference. This is the simplest approach. You run predictions on a large chunk of data at a scheduled time, maybe once a night or once an hour. It is a good fit when you don't need instant results. For example, an e-commerce company might run its recommendation model overnight, generate a list of suggested products for every user, and cache those results so they are ready to display the next morning. Batch is efficient, cost friendly, and easy to manage. And the second is real time APIs. Here the model sits behind an API endpoint, usually REST or gRPC, and serves predictions one request at a time on demand. This is what you need when speed matters. And think about fraud detection. When someone swipes a credit card, the system needs to decide within milliseconds whether the transaction looks legitimate. That's real-time inference in action. And the third is streaming inference. In this setup, your model processes a continuous flow of events as they happen. This typically uses tools like Apache Kafka or Apache Flink. It's powerful for situations like live anomaly detection, say spotting unusual activity on a network in real time, or personalizing a user's experience on a website as they browse. And the fourth is edge deployment. This means running your model directly on a device, like a smartphone, a sensor, or a camera. Instead of sending data to a server, you would instead of serving data to a server, you can run this on your device. So you would choose this when you need very low latency with no network delay, or when data privacy means you can't send user data to, let's say, a outside cloud. Common examples include voice assistant on your phone or health monitoring apps on a smartwatch. So, which patterns you should use? It depends on on your situation. Like how fast the response need to be, how much data you are handling, what your budget looks like, and what your application requires. And in many real world systems, you will actually use more than one pattern together. Batch for heavy lifting and real time for the urgent decisions. Here's something that experienced machine learning engineers learn quickly. Deploying a model is not the end of the job. It's actually where the real work begins. Why? Because the real world is always changing. Customer behavior shifts, market trends evolve, new patterns appear in your data, and a model that worked great at launch can slowly become less accurate without anyone noticing, unless you are watching for it. That's what monitoring is all about. So let me explain the main things you need to track. The first is data drift. This happens when the data coming into your model starts looking different from the data it was trained on. For example, imagine you trained a model using shopping data from before the pandemic. So the post-pandemic shopping behavior is very different compared to the pre-pandemic. More online purchases, different product categories. If the input data shifts like this and you don't catch it, your model's prediction will quietly get worse. Data drift detection helps you spot this early. The second is concept drift. This one is a bit trickier. Concept drift means the relationship between your input features and the outcome has changed. The same inputs now lead to different results. For instance, the features that used to predict Loan defaults reliably might lose their power when economic conditions change, like during a recession. The data looks the same on the surface, but the meaning behind it has shifted. Beyond drift, you also need to track performance. That means monitoring your key metrics like accuracy, precision, recall, or whatever business metrics you care about. And it should be also on live production data, not just on your original test set. You also need latency monitoring. Latency just means how long it takes your model to respond. Even if your model is highly accurate, if it takes too long to return a prediction, it can hurt user experience or break downstream workflows. And finally, automated training triggers. In a well-designed system, you set clear thresholds. For example, if accuracy drops below a certain number, or if drift goes beyond above a certain level, the system automatically starts a retraining pipeline. No one needs to manually check and fix things. The system takes care of itself. So this is what separates a quick prototype from a production grade system. A mature machine learning system doesn't just run, it adapts, it evolves, and that ongoing optimization is what keeps your business value growing over time. Let me bring everything together with two real world examples. These will show you how all the pieces we have discussed work together in practice. So example one is an e-commerce recommendation engine. The model at the center could be a collaborative filtering model or a deep learning recommender. Its job is to predict which products a customer is most likely to click on or buy. But the model alone isn't enough. Here's what the system around it looks like. So the data pipeline pulls in clickstream data, purchases history, and browsing behavior in real time. A feature store calculate things like user embeddings and product embeddings. Those are the numerical representations that capture user preferences and product characteristics. The model gets retrained every week on the latest interaction data, so it stays current. Batch inference runs overnight to pre-compute recommendations for all users, while a real-time API adjusts those recommendations during a session based on what the user is doing right now. And monitoring tracks metrics like click-through rate and revenue per recommendation. If those numbers drop, the system triggers a retraining cycle. The end result is millions of users get personalized shopping experiences, and the system continuously optimizes itself, driving steady growth in conversation and revenue. And the next one is a credit risk model in banking. So the model's job is to score loan applications based on factors like credit history, income level, and employment data, and also transaction patterns. Now let's look at the system. The data pipelines are tightly controlled because banking has strict regulations around data handling and compliance. Feature engineering is standardized and fully auditable, meaning you can trace exactly how every feature was calculated. The model is served through a real-time API that's plugged directly into the loan application workflow. So decisions happen instantly. Every single prediction is logged for regulatory reasons, because regulators need to understand why a particular decision was made, which is called explainability. Monitoring tracks not just accuracy but also approval rates, default rates, and fairness metrics across different demographic groups. Concept drift detection makes sure the model adapts when economic conditions change, and the model registry keeps a complete audit trail of every model version that's ever been used. The end result is fast and more consistent lending decisions, lower risk, full regulatory confidence, and the ability to scale lending operations without needing to proportionally increase human reviewers. In both examples, the model is essential, but the system is what turns that intelligence into compounding business value. So models create predictions, systems create impact. If you are building machine learning solutions, I would encourage you to always think beyond the model itself. Think about the data pipelines that feed it, think the infrastructure that serves it, the monitoring that watches over it, and the feedback loops that help it improve. So this kind of system thinking is what transforms a proof of concept into an actual product. And it's what separates teams that just experiment from teams that ship real solutions. Build your models with care, build your systems with intention. That's how you unlock real value. If you found this helpful, go ahead and subscribe. I'll be doing more deep dives on production ML, system design, and engineering best practices.